right, good morning. Welcome back. I hope you guys are all doing well and staying safe. Looking for a few people today, but I'll go through that in a second. Just a little heads up. I'm sitting in the classroom. This is your classroom. Right now, there's only one person in the classroom. No big deal. Just want to show you what it looks like in this classroom before we return here. So when we return back to class, you'll see it's going to look like this. It's a Red Academy, 3rd floor, glass classroom on the end. So if you want to come back to class, you'll see this classroom, and you'll find this room. Once you come to the classroom, you'll wear a mask. You'll go through all the routine. It's a big class. I wanted to show you that. It's a big class. If you come back, I will spread you guys out, and you'll sit like every other seat, at least a distance away from people, just so you can have some space and you're not breathing down someone's neck. So I will definitely spread you guys out once you get back to class or to this classroom if you want to. You know, Monday, May 3rd, if you're in 10th grade, you have the ability to come back if you want to. This is the classroom we'll be at. Come back to class, we're wearing a mask. I'll wear my mask too. There's Chrome card up here. There's sanitizer. There's some spray and some paper towels if you want to use that. You can sanitize your desk. You can sanitize your Chromebook, your keys, all that stuff if you want to. This classroom will be a safe atmosphere. Its routine is going to be very similar to what we're doing right now in class. So unless I have the full population in class, then my routine is going to continue the same way. Hey, Alex, good morning. Welcome back. Does anybody have any questions for me? All right, Faithy, thank you for letting me know. Anybody, any questions for me for today? All right, I'm looking for a couple people. I'm looking for Tristan. I'm looking for it's here. Nidal. Tristan and Nidal, if you're here, please let me know. Throw your name in the chat. Just let me know if you're here. Someone asked, what if we start notes online, then go back to school? If you want to do your notes online, you could still do your notes on Google Docs. There's Chromebooks here for each and every one of you guys. You can't bring your own Chromebook in. If you come back to school, you have the ability to do your hard copy notes, or you could do them online, the routine we've been doing. So some of you guys may want a piece of paper and pencil. It's been a while since you used that copy. You could complete them on a piece of paper if you want, or you could do them on Google Docs. So you have that choice. If you started as the basis online and you come to school on Monday, I'll give you a hard copy. If you want a hard copy, you can pick up where we left off. You don't have to copy everything in your notes from the beginning of the unit. You can submit what you have. I'll figure out that correlation where you left off. And obviously you should have the full copy somewhere between both the digital copy and the hard copy of notes. Hopefully that helped you. Okay, let's check out the COVID report for today. Analyzing COVID in Oneida County. Right now in Oneida County, there's 389 cases of COVID in the county and 20,588 resolved cases in the county. The cases went up a few from last class, yesterday. Number of deaths, there's 416 people that passed away from COVID. Hospitalization numbers have increased by a little bit, a little weird correlation there. 21 people in the hospital, and now there's 5 people in ICU. Vaccine numbers are increasing, but not quick enough, in my opinion. New York State, we started off strong with vaccinating for vaccines, but now we kind of slowed down that process. Not as many people in Oneida County are getting vaccinated as the rate maybe about 3 weeks ago or so. 50.9% of the people that are 16 and above have their first dose of vaccine. Total vaccines, 2 shots, 40.8% people are vaccinated, fully vaccinated in the county that are above 16. If you are 16 and above and want to get vaccinated, check out the Oneida County website. There's different pods, different locations where you get vaccinated throughout the area. All right, check out the daily numbers. Number of cases per day. Checking out the tail end of this curve, doesn't look that bad. On the 26th, there were 34 cases. On the 25th, 26th, 25th, there was 15 cases. Good. The day before that, there was 30. You can see the rest of this. Those numbers the last week have been amazing. Hopefully, we can stay below 40. Hopefully, get below 30. So that is definitely heading in the right direction. The more people that get vaccinated, the lower this mark will be. President Biden is going to be making a speech tonight. They're talking about the CDC lowering. They already did talk about the CDC lower the guidelines for mask mandates for at least out in public. You can check all that out if you want to as well. So things are definitely looking brighter for us. Let's figure out what's happening for the best class of the day. Here we go. The classroom page. Quote of the week comes from an unknown source. Life is like a camera. Just focus on what's important. Capture the good times. Develop from the negatives. If things don't work out, take another shot. Get back up. Take another shot. I like that quote. Unknown source. Today's Wednesday, April 28th, 2021. It's a day one. We're going to continue on with unit number 9, which is acid, bases, and salts. We'll go through topic number 3, which is Lewis acid and bases. Really quickly, we'll go through that. We'll watch a YouTube flick on different theories for acids and bases. We'll take some notes on Lewis. And then we'll jump into topic number 4, which is the pH scale and indicators. We're really going to focus on just the pH scale today. Next class, we'll jump into indicators. We'll watch a YouTube flick. We'll go through some guided notes, and then there will be some examples. That's the type right there. On topic number 4 for pH scale and indicators. We probably will not get through the examples today. There will be some examples. There will be some exit pass questions regarding pH scale. Notice topic number 3, there's no examples, there's no exit pass questions that need to complete for that unit. Below you can see the attachments. We have the reference table, we have 2 flicks. That is what's going to happen for today's class. All right, quick review before we jump into that video. I'm going to open up my guided notes. Let's analyze where we were. What did we go through so far? All right, so far we went through 2 theories for acids and bases. We went through Arrhenius theory for acid-base. We went through Bronsted-Lowry theory for acid and base as well. You finish the examples, you finish the exit pass for them too. Today we'll be going through Lewis acid-base theory. So we will be doing this portion, topic 3. We will also start to get through the pH scale as well. So Arrhenius theory, what do we know about Arrhenius theory? We know about the basic properties for acids and bases. We know that acids are sour. We know bases are bitter. But Arrhenius theory more so talked about acids being hydronium and bases being hydroxide. We analyzed some common acids, we analyzed some common base. We filled out this chart on the bottom for Arrhenius theory for acids and bases. Hydronium, acid, hydroxide, base. Done. That's one theory. Second theory we went through yesterday. We talked about Bronsted-Lowry theory. You saw how we did this process. We said an acid's a hydrogen ion donor or proton donor. A base is a hydrogen ion or proton acceptor. We highlighted this box. We figured out which 2 were paired up together or most similar. The 2 blue boxes are similar. The 2 red boxes are similar. We analyzed the reactant side of the equation. We figured out what happened between these 2 boxes. What's the difference between these 2 boxes? We figured out which one's accepting the H. We figured out which one's donating an H. We talked about conjugate acid and bases. We labeled it with an example. And then we figured out some acid-base pairs. And then we figured out what the Bronsted-Lowry theory for acid and base was. Let's pick up with a video. So today's class, we're going to start off with a video regarding a couple theories for acid and bases. Here we go.
you encounter acids and bases, and you probably ate food with acids in it today and maybe washed the dishes with a base. There are some basic properties that will help you distinguish acids and bases from other chemicals. Acids have a sour or tart taste. Think of lemons or vinegar. That's the taste. Bases taste bitter, which is not a pleasant taste. If you've ever had soap in your mouth, you'll know the taste of a base. Both acids and bases will change color in the presence of an acid-base indicator. They both can be strong or weak electrolytes in solution, and they're both corrosive. Always check the safety information when working with acids and bases to make sure that you protect yourself and your clothing. Acids also have a slightly different naming convention compared to other chemicals. Here are some common acid names that you'll come across in the chemistry lab. Now, it wasn't until the late 1800s that a scientist was able to propose a theory for what makes an acid and a base a base. That scientist was Svante Arrhenius. He said that acids are hydrogen-containing compounds that ionize to create hydrogen ions, or hydronium, in solution, and bases are compounds that ionize to create hydroxide ions in solution. Let's look at an example of this happening. Hydrochloric acid is a hydrogen atom and a chlorine atom covalently bonded. In water, the hydrogen abandons the chlorine, leaving its electron behind, and then it joins the water molecule to form hydronium ion. Because hydrogen can be removed as an ion, hydrochloric acid is ionizable. Hydrochloric acid releases one hydrogen, so it's called monoprotic. Some acids have multiple hydrogen atoms that will ionize and could be diprotic if they release two hydrogen ions, like sulfuric acid, or triprotic if they release three hydrogen ions, like phosphoric acid. Let's look again at hydrochloric acid in water. Hydrochloric acid is an Arrhenius acid because it creates a hydrogen ion. The hydrogen ion immediately attached itself to water to form hydronium, H3O+, which is the aqueous form of hydrogen ion. Arrhenius bases produce hydroxide, so it's no surprise that all of these bases have hydroxide in their names. Potassium hydroxide and sodium hydroxide are strong bases and are very soluble. Calcium hydroxide and magnesium hydroxide are also strong bases, but they don't dissolve easily in water, which makes the solution very diluted with hydroxide ions compared to the highly concentrated ones that are in potassium hydroxide and sodium hydroxide. Now let's look at a base in water. We'll use sodium hydroxide. Sodium hydroxide is a sodium attached to an oxygen and hydrogen, which is the hydroxide ion. And when it breaks apart in water, you'll get a sodium ion and a hydroxide ion. That hydroxide ion is what makes this a base. Because the sodium hydroxide was able to make that, it's an Arrhenius base. The Arrhenius definition, it turns out, is too confining for all acids and bases. For example, ammonia is basic, but there's no hydroxide on ammonia. In the presence of water, however, it will react to produce hydroxide from the water molecule. So there is another way to define acids and bases. The Bronsted-Lowry definition is that acids are hydrogen ion donors and bases are hydrogen ion acceptors. It's a broader definition. So all Arrhenius acids and bases are also Bronsted-Lowry acids and bases, but not all Bronsted-Lowry acids and bases are Arrhenius. When you look at an acid-base reaction, you'll notice that a double arrow is often used. This implies that the reaction is actually reversible.
Let's take a look at this reaction again. So this chemical reaction, we're trying to figure out which one's a Bronsted-Lowry acid, which one's a Bronsted-Lowry base. When we went through this equation, or these types of equations yesterday in class, the first thing I told you to do was to highlight one compound, like NH3. And then I said, hey, what's NH3 most similar to? NH3 is most similar to NH4. They're pretty darn close. NH3, NH4, the difference is only one H. Those two red boxes would be called Bronsted-Lowry pairs, acid-base pair. Additionally, I said check out the next compounds here, like H2O. H2O is most similar to OH. Those two would be a Bronsted-Lowry acid-base pair. They're paired up. They're most similar. You can easily identify that. Now we had to go take it a step further. We had to figure out which one's donating, which one's accepting an H. So I told you, check out the 2 red boxes and figure out what's going on from NH3 to NH4. What's happening when you hit the forward reaction from NH3 to NH4? You guys could tell there's 3 H's here, there's 4 H's there. How do we get the 4 H's to the right side? You had to take an H from H2O and add it to the NH3. That right there tells you which one's accepting, which one's donating an H in the chemical equation. So again, H was donated from H2O, and the one that's going to accept it is NH3. Donors, acceptor. The one that donated was going to be the acid. The colors didn't work out here. This is going to be the acid, donor. The one that accepts is going to be the base. We should also understand, whatever the base is, follow that little bracket. The other red box over here is going to be my conjugate acid. They're opposites. Whatever my acid is going to be my conjugate base. Opposites in that order too. You should be familiar with that process from yesterday's class.
It can occur in both directions. In this reaction, the ammonia is the base because it's the hydrogen acceptor. By default, then, the water is acting as an acid because it will be the hydrogen donor. But when we look at the other side of the equation, we could imagine it going to the opposite direction, where ammonium ion would donate the proton and hydroxide would accept. We call these the conjugate acid and the conjugate base. A conjugate acid is the particle that's formed when a base gains a hydrogen ion. And a conjugate base is the particle that remains when an acid has donated a hydrogen ion. They will always be paired like this because it's a reversible reaction. In this scenario, the hydrochloric acid has a conjugate base of chloride ion, and the water is the base to hydronium as the conjugate acid. With ammonia, however, water acted as an acid. Water is incredibly special for many reasons, and one of those is that it's amphoteric. It's able to act as both an acid and a base. If you break off one of the hydrogen atoms, you get a hydrogen ion and a hydroxide ion. The hydrogen ion would imply that water is an acid, and the hydroxide would imply that water is a base. And the truth is, it's both. Amphoteric. Pretty amazing. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe and follow me.
All right, so there's more information about Bronsted-Lowry and Arrhenius acid-base theory. Please open up your guided notes. Go to unit number 9, acid bases and salts. And let's pick up where we left off with Lewis acids and bases. So again, 3 theories. First theory, Arrhenius, done. We talked about Bronsted-Lowry, done. And today we're going to cover Lewis acid-base theory. It's a quick one. It's not going to take too long to go through this. Before I jump into the theory, you see Lewis, it's chemistry class. Hopefully you remember Lewis with the Lewis dot diagrams. Let's do a little refresher for a second. So Lewis in chemistry class, hopefully you think of the Lewis dot diagrams. Hopefully you think of the reference table. Hopefully you can make a Lewis dot diagram for any element. Let's practice this again. So a Lewis dot diagram, if they ask you to represent a Lewis dot diagram for an element, you should be able to do this. It's getting close to the end of the year, so let's review how to do a Lewis dot diagram for the atom of Mg. So we're focusing on Mg. If they ask you on the post test, draw a Lewis dot diagram for Mg, you should be able to do it. So Mg is a symbol. That's the mass. That's the average of all the naturally occurring isotopes. This is my atomic number or proton number. And the number on the bottom is my electron configuration. If you add them all together, it tells you the total number of electrons that the atom would have. If they ask for a Lewis dot diagram for the atom of Mg, atom of magnesium, you should know you're going to have the symbol, which would be the kernel. Mg's the symbol. The kernel represents the protons, the neutrons, and the non-valence electrons. So that represents protons, neutrons, and the non-valence electrons. So these two electrons here, these two shells electrons, 2-8, are the non-valence electrons. So kernel represents protons, neutrons, and non-valence electrons. For a Lewis dot diagram, what do we represent? We represent the valence electrons in the outermost shell. In this situation, how many valence electrons are there? There are 2. 1, 2. This is a Lewis dot diagram for the atom of magnesium. Atom's charge equals 0. Why? Talked about this quite a bit last unit. Atom's charge equals 0 because the protons and electrons cancel out. If there are 12 protons, there must be 12 electrons. This is a Lewis dot diagram for the atom of magnesium. Hopefully you can do that. Lewis dot diagrams represent valence electrons. If they ask you on the regions to represent, or if they ask you on the post test, they ask you about representing the ion for magnesium, a Lewis dot diagram for the ion of magnesium, hopefully you can do that too. If they ask for the ion of magnesium, an ion is an atom with a charge. So it's going to be magnesium. The kernel is magnesium again, Mg. Ion is an atom with a charge because it either lost or gained some electrons. Ion of magnesium, look at the top right corner. The charge is going to be represented. That's going to be +2. What does that +2 mean? It doesn't mean you add 2 electrons, but rather you take 2 electrons away. So you lose 2 electrons in that situation. What 2 electrons? The 2 electrons in the valence shell. Those 2 right there in the diagram. So if they ask for a Lewis dot diagram for the ion of magnesium, you represent the symbol. I always put brackets in there. And then the charge is +2, which means it lost the 2 electrons. The 2 electrons at the atom head are now lost. Main thing here, I'm trying to get you to think, Lewis dealt with valence electrons. Lewis dealt with electrons here. Go back to the notes. Here we go. Talking about the Lewis theory for acids and bases. Scroll on down. Here we go. This section of notes is going to go really quick. Lewis acid-base theory. Lewis proposed that acids accept a pair of electrons and bases donate a pair of electrons. So again, he's referring to the electrons again. This guy really loves studying those electrons. So again, I'm cap locking, I'm bolding, I'm highlighting. Lewis proposed that an acids accept a pair of electrons Lewis talked about electrons and acids accepting a pair of electrons during a reaction, while the bases are going to do the opposite. Bases are going to donate a pair of electrons. So one again accepts, the other one donates. Bases donate. So again, I leave my acids red, I leave my bases blue. You'll soon see why, especially when you talk about the pH scale. Similar to Bronsted-Lowry's theory. Bronsted-Lowry talked about protons or H+. Someone's donating, someone's accepting. But Lewis's theory is talking about electrons. Someone's donating, someone's accepting a pair of electrons. So the concepts here are a little bit different. A Lewis acid. Lewis acid base. Lewis acid, a little repetitive here. A substance that can accept a pair of electrons to form a covalent bond. Accept a pair of electrons to form a covalent bond. We should know a covalent bond. Covalent bond, two nonmetals. They share electrons. They have electronegativity less than 1.7. There could be polar, there could be nonpolar. Hopefully you remember that stuff. Lewis acid is a substance that accepts a pair of electrons to form a covalent bond. A Lewis base, a substance that donates a pair of electrons to form another covalent bond. So you should be aware of which one donates, which one accepts. Let's analyze an example. Lewis acid base example. In this text box below, we're going to draw the information here. We'll write it in. All right, so in this text box, please click on it. We're going to draw a little image in here. Go to Insert, Drawing, New. And this is going to be the chemical reaction that we'll analyze for Lewis acid-base theory. So please click on the text box. We'll make a nice horizontal text box. Nice long one. I'm going to make my font a little bit bigger. I'm going to center it. I'm going to bold it. Just so we can analyze this chemical reaction. It's an easy one. We have H+, so hydrogen ion, hydrogen cation, plus hydroxide, OH negative, yields, the forward reaction, yields water. Hey, Tristan. Hope you're okay. We're taking some notes on topic number 3. Yields to make water. Let's check out this process. Let's see what's happening here with the Lewis dot diagram. So H plus OH negative yields to make water. What I'm going to do, I'm going to ask that we copy and paste this text box that we just created, copy it, and paste it below. All right. So copy that text box, Control C, paste it below, Control V. This time we're representing this equation with Lewis dots, or the electrons. In this text box, I'm going to ask that we spread out each of the elements a little bit so we can fit some more information here. We'll focus on each element and the electrons represented. H+, think about hydrogen for a second. How many valence electrons does H have? It has 1 dot. If it's a plus, it means it's going to become positive. How does it become positive? You take 1 electron away, throw it away, it becomes a positively charged. So that first ion has no electrons around it. Oxygen, on the other hand, will have some around it. How many valence electrons does oxygen have? Anybody? Throw in the chat, unmute. How many valence electrons does oxygen have? Oh, check out the reference table. How many valence electrons does oxygen have? How many dots? How many valence electrons does O have? Use the reference table. Open it up. Find O. How many valence electrons does O have? Thanks, Joseph. O. Thanks, Alex. Oh. Oh. Gotcha, Alex. O has 6 valence electrons. 6 electrons in the outermost shell. Nitrogen has 5. Carbon has 4 valence electrons. Fluorine has 7. Oxygen has 6 valence electrons. Next thing we're going to do, we're going to go to shapes. We're going to go to oval. I'm going to make a small electron. Make a small circle. That's going to be my electron. Small circle. Make an electron. Make a small little dot. Going with it. I'm going to fill it in black so it pops out a little bit more. So use a paint can, fill it in black. We need 6 electrons. You guys saw that there's 6 electrons for O. I'm going to copy that image by hitting Control C. So click on it, hit Control C, and paste it 5 more times by hitting Control V. 1, Control V, 2, 3, 4, 5. The placement of the electrons. We should know 1 goes to the north side. 1 goes to the east side. 1 to the south side. 1 to the west side. That's the placement of the first 4 electrons. The 5th one would be paired up at the north side. The 6th would be paired to the west. I'm sorry, the east side. And then what's going to happen here, there is room for 2 more electrons. That H minus is going to indicate 2 more electrons coming in. H originally has 1 valence electron. That minus sign means that 1 more electron would come into play. So if I take another electron, that's going to be another electron. So I'm going to paste 2 more electrons by hitting Control V 2 more times. This time I'm going to paint it a different color just to indicate it's coming from somewhere else. So I'll paint it red. So the last 2 electrons would come into play right there. 1 to the south, 1 to the west. Boom. That is now a stable octet. We can see that the O took in electrons and the H gave off the electrons. You can figure out one's accepting one is accepting electron, one is releasing electrons. We'll label that in a second. Next up, I'm going to draw a Lewis dot diagram for water. I got rid of the 2, I'm going to spread out the O. I'm going to copy 8 more electrons in here. We're going to put the 8 dots around here again. I couldn't really copy and paste this over. If you can, go for it. I'm going to paste 8 more electrons. 1, 2, 3, 4, 5, 6, 7, 8. And place the electrons around the O. Same way, we should know how to put the electrons around an element. 1 to the north, 1 to the east. You could do this on a separate piece of paper. Yes, definitely. Do not forget to upload your images. By now, you realize that these notes drive our class. If you are paying attention to the notes, if you're completing your notes, somewhat engaged the class, then you understand what's going on in this class. You understand the examples. You understand the exit pass. You probably understand the benchmark exam too. If you're doing what I ask you to do, you're probably doing really well in this class. And a lot of you guys are really doing well. So thank you. I know this year has not been easy. It's a tough world we're in. It's tough learning at home. I know it is. It's tough teaching from home with my kids in the other room and they're not going to get in. I know you have distractions. That's why I record the classes. That's why you can rewatch it. I give you a little flexibility there for assignments as well. I can't get this electron to move over. Come on. I'll have to fix that later. All right, so there's the 6th, 7th, And then I'm going to indicate the last 2 electrons in red to say that they came from somewhere else. Last 2 electrons, one to the south and one to the west. So you can see what's going on here in this situation with water. There's going to be 2 H's. Each one of the H is going to have a red electron that's going to give off. Wish these were a little tighter, but I'm going to go with it. The last thing I need in this diagram is another H. Each chemical equation, reaction, must obey the law of conservation of mass, energy, and charge. Make sure it does. My last electron I'll place right there. This is a Lewis dot diagram for H2O. You can see what's going on here in this Lewis acid-base concept. We should be able to figure out which one's a Lewis acid and which one is a Lewis base. Last thing, I'm going to label my Lewis acid, Lewis base below. The H plus is a Lewis base. Lewis base. Why is it a Lewis base? Because it's donating its electron. Lewis base because it's donating the electron. The OH is going to be the Lewis acid. Whoops. Lewis acid. Why is it Lewis acid? Because it's accepting the pair of electrons. All right, folks, that's the image that I wanted you to create here. Hopefully you can see the donation or the acceptance of the electrons here for Lewis concept of acid and bases. You have that image, please save it and close it, put it into your notes. One thing about these notes, we're able to color code these really easily. And my images, I get to restore it, show you how to cut it and paste it every time, all that good stuff. Hopefully you don't have that problem. Hopefully it's just a Mr. Brown problem. There it is. All right, so that's the example for Lewis acid and base that I want you to have in your notes. So again, one's going to accept the pair of electrons, one's going to donate a pair of electrons. Last thing for Lewis acids and bases, I'm going to try to squeeze this in somewhere in this area, on this page. There's a little toolbar below. I'm going to just press delete a couple times so I can sneak it in. That should do the trick. So Lewis acid, Lewis base. Major concepts. I'm going to paint the acids red. Acid is going to be accepts electron pair. Lewis acids, excuse me, accepts electron pair. Lewis acid accepts the electron pair. On the other hand, the Lewis base is going to donate an electron pair. Donate electron pair. That is topic number 3. Are they going to ask any questions on the benchmark on Lewis acid, Lewis bases? No. Are they going to ask any questions on the post-test on Lewis acid bases? No. The reason why I put this in here is because there are 3 theories for acid bases, and I figured might as well just cram this one in too. This, good to know for AP Chem. Only time it'd be single if there's, somebody asked a question. Only time it'd be single if there's only 4 electron total. Yeah, they should be paired up if it's a stable octet. All right, next page. Here we go. I'm going to ask that you copy down the theories for acids and bases. This is like the little key for each of the 3 topics. You have the keys above, the little charts above. Please copy and paste those sections for Arrhenius, Bronsted, Lowry, and Lewis. So what am I talking about? I'm just going to go to each topic above. I'm going to copy. I'm going to paste the theory. It's the last thing I put in the notes for the topic. So Arrhenius. Check out Arrhenius. There's the theory. We should know Arrhenius theory. Acids are H plus or hydronium. The bases are OH negative or hydroxide. So again, took the Arrhenius theory. I'm going to copy and paste it right there. Change the font. Arrhenius theory for acid bases. Acid is H plus or hydronium. A base is hydroxide or OH. Bronsted-Lowry theory, acid bases. Talked about proton or H plus, donating or accepting electrons. Donating or accepting a proton. Sorry, not electrons. Bronsted-Lowry theory for acid bases, an H plus or proton donor is an acid. A base is an H plus or proton acceptor. And a Lewis theory, it's right above. Just copy and paste that. This is a nice little cheat sheet to differentiate the 3 theories for acids and bases. The theories they do like to talk about are Arrhenius and Bronsted-Lowry theory. Those 2 know inside and out. Lewis, not so much. All right, a little bit more information on reactivity with acids and a metal. Last unit, we analyzed table J. This table J, in the reference table, we talked about with redox. It says most active metals on the top, least active metals on the bottom. And we said with redox, the metal that's higher up is the anode, the metal that's lower is the cathode. Now talking about these metals with acids. So notice that most active elements come from group 1 or group 2. Least active metals come from the transition metals like silver, gold, copper. Oh, H2 is on there. That's not a metal. So H2 is on there for a different purpose. H2 is hydrogen gas. We'll talk about that concept right now. The elements higher on the chart. The elements higher on the chart. Elements higher on the chart will react with an ion or elements below it. With the ion of any element below it. So table J is telling you about reactivity as well. Not just, it's reactivity, how reactive it is. Elements that's higher on the chart will react with an ion or an ion of any element below it. Excuse me. Ion of any element below it. Hydrogen gas, H2. You can see on the chart, H2. It's hydrogen gas. It's also a diatomic molecule. closer to the bottom of the chart, which is found near the bottom of the table. Therefore, any metal above it above hydrogen in the table will react with a hydrogen ion and acids to produce H2 and salt. So hydrogen gas, very present in the atmosphere, H2, hydrogen. When hydrogen reacts with lithium, it's going to react. Hydrogen reacts with rubidium, it's going to react. Potassium, cesium, barium, strontium, calcium, they're going to react. H is right there, where my cursor is. When H reacts with any of the ones above, there's going to be some sort of reaction. H plus, you think of H plus as being the acid. Acid reacts with any of these above, it's going to be reactive. H plus, or hydrogen gas, reacts with copper, silver, or gold. It's not going to be very reactive. That's why we take some gold to make jewelry. That's why we take silver to make jewelry. It's not going to be very reactive in the atmosphere. Copper, which is below hydrogen gas, will not react with hydrogen ions and acid. Copper, which is below hydrogen, will not react with that. So note, hydrogen gas is the only element that is a nonmetal on that side of the chart. All right, moving on forward. Here we go. Next topic. So again, this portion right here, there's no questions regarding this. I wouldn't anticipate to see any questions regarding this on the postmark either. Post-test. Topic 4 is going to be about pH scale. So from now to the rest of the class, we're going to start to put a pH scale in, about 35 minutes. We'll go through indicators next class. We'll figure out what these indicators even mean. Maybe play baseball, maybe play softball. You hit the ball, you're on first base. Maybe the first base or third base coach gives you a sign. What's the sign? Is it going to be stealing? Is it going to be hit and run? Is it a bunt? There's an indicator probably for the sign giver. Whoever's giving the signs in third base, there's probably a sign. There's an indicator that tells you to steal. Indicator tells you to bunt, whatever it may be. But we'll go through that next time. pH scale is going to be the next topic we're going through. We know some information about the pH scale. 8th grade science, we know pH scale goes from 0 to 14. You might know the location of acids. You might know the location of bases. Before we do the pH scale, let's watch a flick on information regarding this topic. pH scale, here we go.
In today's video, we're going to look at the pH scale and see what acids and alkalis are. pH is really just a measure of how acidic or alkaline a solution is, and it's measured on a scale from 0 to 14, with low numbers being most acidic and high numbers being most alkaline. And if the substance is neutral, like pure water, then the pH would be 7, which is neither acidic nor alkaline. To give you some idea of what all of this means, the acid in your stomach, which helps you to kill bacteria, has a pH of around 2, while acid rain is around pH 4. Then for alkalis, washing up liquid has a pH of around 9, and the bleach we use to clean bathrooms has a pH of around 12. Be aware though, you don't have to remember these specific examples. They're just to give you some context. Now, we can measure pH in a couple of different ways. One is to use some kind of indicator, which are a group of chemical dyes that change color depending on the pH. And different indicators will change color at different pHs. Some indicators contain a mixture of these different dyes though, so their color will slowly change across a wide range of pHs. So we often refer to them as wide range indicators. The most common example is universal indicator, which gives the colors we've shown on our pH scale here, ranging from deep red at a very low and acidic pH, to yellow, green, and then bluey purple as we increase the pH and it becomes more alkaline. The other way to measure pH is to use a pH probe connected to a pH meter. By dipping the probe into a solution, we can electronically measure the pH and get a numerical reading on the meter. The benefit of the probe compared to an indicator is that it can be much more accurate and precise, because it doesn't involve humans guessing shades or particular colors. And as a general rule, measurements that remove the need for human judgment are going to be more reliable. The next thing we need to look at is what exactly makes something an acid. You can define an acid as any substance that forms aqueous solutions with a pH of less than 7. And the reason for this is that acids release hydrogen ions in water, which make the solution acidic. On the other side of the scale, we have bases, which we define as any substance with a pH greater than 7. Meanwhile, alkalis, which we mentioned before, are actually a subgroup of bases that are soluble in water. So we would say that an alkali is a base that dissolves in water to form a solution with a pH greater than 7. And these alkalis form OH- ions in water, which we call hydroxide ions. If we react an acid and a base together, then we get a neutralization reaction, which will always produce a salt and water. For example, hydrochloric acid plus sodium hydroxide, which are the most common acid and base, will react to form sodium chloride, which is a salt, plus water. Reaction hydrogen ions and hydroxide ions, where H+ from the acid and OH- from the base combine to form H2O. And because the acid and base have both been neutralized in these sorts of reactions, the pH of the products should be 7 because they're neutral. Before we finish, I just want to point out some of the common acids and bases that you'll come across in the course. The main acids are hydrochloric acid, sulfuric acid, and nitric acid, while the common bases are generally hydroxides or carbonates, like sodium hydroxide or calcium carbonate. There are loads more, but it's definitely worth learning these few, as they crop up a lot. Anyway, that's all for today. So hope you enjoyed this video, and we'll see you next time.
All right, pH scale, acids, and bases. pH is a big test they do a lot of time for chemistry. They do a lot of quantitative testing with pHs. Why do they do pH so often? It's a quick little reference to see if something's going to harm you. Is it safe for you? When I work as a chemist at the FX Matt Brewery, let's talk about the process for a second. We did the several testing. Each product had about 12 different tests for each product. If you ever toured the brewery, you know how massive it is. You know how big that facility is. And there's a lot of products in the big tanks. If you haven't seen it, it's worth the $5 investment. Go check it out. It's in your backyard. They'll give you a root beer at the end. But anyways, what happens? At the FX Matt Brewery, it starts off, you go to the tour, and then you see these big copper kettles. So it's like a big kettle. You walk into the brewery, you're like, wow, that's pretty shiny. That's pretty cool. And inside those kettles, they cook the product. They start off the product. They take some wheat, grain, water, other stuff. They mix it together to start the process of making soda or the stuff that maybe your parents consume when you're over 21. So they put a bunch of products in there. In this situation, it is going to be a heterogeneous mixture. There's several things that are mixed together. They light it up. They're heating it up. There's flame below, some sort of heat source below that's heating it up. And once it heats up, we know what's going to happen. Liquid's going to start to heat up. The boiling point's going to increase. You're going to have some sort of vapors escaping as well. Once it reaches a certain boiling point, what happens next? They bring it to a different tank. They transfer it to a different location. So they put it into like a tube or some sort of way to transport to something else. This has to be clean. If it's not clean, then there could be bacteria inside. The kettle has to be clean, or there could be some sort of bacteria inside that could ruin the product. If it's not clean, I would know it, or the chemist would know it, because the pH level wouldn't be the same, or the other testing wouldn't be the right values. They compare the values, make sure it's running the right pace, so you make a right product. So transfer to the next station, next big tank. And in this tank, what's going to happen, they're going to basically funnel it all out. Funnel out the solid sediments from the liquid sediments. So think about the process of maybe just taking all that liquid inside that copper kettle, pour it in a funnel, and then what's going to happen, you know that there's going to be solid sediments forming on the top. And we also know that a liquid's going to form on the bottom. So if I took that concept with a beaker, funnel, we would know that a liquid would form on the bottom half. That cleaner, now that's more like a homogeneous mixture. That cleaner solution is now transferred to another tank. So that's transferred from this tank, I know it's only a beaker, to by hose, by clean hose. How do they clean the hose? How do they clean the tank? They use a strong base, a solution of sodium hydroxide. So that kills the bacteria, that kills anything that may be growing or might not be clean within these hose or the tanks. So next up, we take it to a different tank. These are like the stainless steel, huge tanks. If you've ever been there, you know what I'm talking about. So next it goes to another station, we'll say. And in the station, you're transferring that homogeneous mixture to this big tank. These are all at certain temperatures as well. That's another factor. Once it's in this tank, they're going to add something else called yeast in this solution. So right now we have a very sugary substance, and now we're adding some yeast to the mixture as well. This process, we're actually going to go through it organic chemistry briefly. This is called the process of fermentation. If you're fermenting something, you're going to have two things formed. You're going to have carbon dioxide, and you're also going to have an alcohol. Alcohol is going to be formed as well. The alcohol, a lot of 21-year-olds, some 21-year-old people consume. After it ferments, it's going to be filtered out again. So it's going to go through a filtration process again, and that's going to be stored into another tank. Following that process of making it more homogeneous again, what's going to happen, it's now ready to be processed, and it's now ready to be put into a bottle. So after the fermenting processing, after it all settles out, the sediments, then it's going to work its way to a bottle, and then you'll have some fresh Saranac root beer or fresh Saranac Shirley Temple. That process right there happens in your own backyard. Check out the Saranac Brewery. If you go to the tour, you'll get some Shirley Temple. That sweet Shirley Temple. My main thing here about this whole spiel, we use sodium hydroxide to clean things out. If it's not clean, we'll know it. They do a lot of testing on the products, so any food plant is going to do a lot of testing on it. Why? They want to make sure it's safe. They want to make sure it tastes right. They want to make sure it's going to be consistent with those qualities. So the Shirley Temple is going to have a specific pH value. It's going to have a certain color. It's going to have a certain density. And if it doesn't match up to the right specifications, then something's wrong, and they may have to revisit this mixture. Same thing for the other products as well. Pretty cool process. So yeah, I did do a lot of testing through each one of those processes. One time we were transferring a product and the pH level was crazy. pH level was not good. It was a lot higher than what it should have been. Why? Because they actually had the sodium hydroxide in the lines. And if that sodium hydroxide went into the bottle without a chemist there to analyze it or someone there to figure that out, then obviously that could be a bad effect for the company. Imagine putting sodium hydroxide into Saranac root beer. Try tasting that. Wouldn't be good. So they had to clean out the lines a little bit more. And once they cleaned out the lines, they neutralized the lines. Then it was a safe product. All right, here we go. Let's go through the pH scale. Let's figure out what the pH scale is. Should be a lot of review. We're going to start it. We're not going to finish this today. The pH indicators we'll go through next time. The next page, there should be a blank text box, a big text box regarding the pH scale. Nothing there, but we'll start to have the basics here from now to the end of class. Please click on the text box. If you want to do this on a separate piece of paper, you can. It's going to be something similar to what's behind me. I know you can't really see this one too well, but it's going to be something similar to this right here. So here we go. Click on the text box. Go to Insert, Drawing, New. All right, first things first, we're going to label it. I'm going to put a text box at the top of the screen. I'm going to call this pH scale. Lowercase p, capital H, scale. A pH scale. What's pH mean? pH means potential hydrogen. So P is going to be potential. The H refers to, it's a capital H because it's a symbol, hydrogen. Potential hydrogen. Maybe you know a little bit about pH. Maybe you have a pool. Maybe you test the pH level in the pool every time. Maybe you have a hot tub. Maybe you test the pH level or the chlorine level in the hot tub. Make sure it's safe. The pool has too much chlorine in there, you'll test it. You put the drops of water in, you fill up the tube of water, you put the drops of water in, shake it up, and you match up to like a color scale. If it has too much chlorine, mom might say, hey, you can't go in yet. Too much chlorine is going to burn your eyes. You may have to retweak your chemicals. You have to change the chemicals you have in there. So pH scale, what do we know about it? It has a range from 0 to 14. I'm going to take a text box, and the text box will make vertical, a narrow vertical text box. The pH scale ranges from 0 to 14. All right, so in this text box, I'm going to just put the numbers 0 to 14. After every number, I'm pressing Enter. Zero to 14 on the pH scale. Yours does not have to look exactly like mine. So pH scale goes from 0 to 14. What do we know about pH scale? We know that acids are going to be from 0 to 6.9. 0 to 7 are going to be acids. So I'm going to color code 0 to 6 in a red font. So I'm going to say those are red. Those are going to be the acids. I'm now going to make a bracket by going to Shapes, Equation, Left Bracket. So I'm going to take this bracket, go from 0 to 6. taking the left bracket on your equations, going from 0 to 6. I'm going to color code this red. I'm going to thicken up my line. That portion of the pH scale is acids, are going to be acids. I'm going to take the text box. I'll make this larger and label this acids. Acids, what do we know about them? We know Arrhenius acids have a lot of H pluses. There's going to be abundant of H pluses. There's going to be several of them. Acids. There could be something called a strong or weak acid, depending on how concentrated, excuse me, how concentrated or how diluted the H pluses are in the equation. There could be strong acids. There's going to be weak acids too. I'm going to take another text box above acids, T, text box. These are going to be strong acids. Closer you are to 0 or 1 are going to be strong acids. What does that mean? It means there's going to be a lot of hydronium. There's going to be a lot of H pluses. High concentration of H plus or hydronium. So you have strong acids that are closer to 0, 1, or 2. The weaker acids are going to be closer to 5 or 6. It's going to be more neutral of a stance. There's not going to be as many hydronium ions in this situation, which we'll draw in here. We'll figure out all the components of this. So strong and weak acids. Bases. Bases range from 8 or 7.01 to 14. So bases, I'm going to highlight 8 to 14. I'm going to color code these blue. Nice perk of having this Google Docs, we could color code things. Now that window from 8 to 14, I'm going to put a bracket by going to equation, left bracket. That bracket goes from 8 to 14. I'm going to color code that blue because bases have been blue this whole time. They're still going to be blue. And I'm going to identify these as bases. Take a text box. These are bases. It's all about the base. Bases we know are going to be soaps. They're going to be hydroxide, lye. It's going to be sodium hydroxide, potassium hydroxide. If you go to the cleaning aisle at Walmart, cleaning aisle at Hannaford, wherever you may go shopping, cleaning aisle at Amazon, you will see several bases in cleaning agents. Bases are used to clean things. Could use an acid to clean things, but typically bases are used to clean things. Soaps. With a base, there could be a strong base, there could be a weak base. What makes a base? Think of Arrhenius. What makes a base? Hydroxide. So if there's a lot of OH negatives, it's going to make a stronger base. Where's a strong base? It's going to be closer to 13 or 14. So I had another text box below. It's just about, oh no. Try that again. Add another text box below. This is going to be strong. A strong base. I'm going to color code that blue again. Getting crazy today. I'm adding a different font in here. So stronger bases, higher ion concentration of hydroxide are at 13 or 14. The weak base is closer to neutralization point. I'm just going to copy and paste my weak from acid and just change the color. So that, we probably know most of that already. Maybe you didn't know about strong or weak acids or bases. Next up, I left that 1,7 black. That is going to be the neutralization point. At that point, it's going to be neutral. At a text box, right in between the acid and base is going to be neutral. You think of something being neutral, you think of water. Distilled water specifically. The neutralization point of water for distilled water is 7.0. But the weird thing is, the water that you consume, it's probably not 7.0 on a pH scale. Water, each water that you have, maybe it's Dasani water, maybe it's Aquafina, maybe it's a Smart Water, maybe it's the tap water from the city, which I drink. They all have different minerals in them. They have different substances put inside them to clean them. For taste, there's different purposes. You ever try Dasani water and Aquafina water and say, hey, these don't taste the same? It's water. Why does it taste the same? There's different things added. So the city water, what they do, they have a water treatment plant, which I would love to visit with you guys, but they won't let us visit there. They won't let any classes visit there. I know this year is kind of different, but they treat the water so bacteria doesn't grow in there. And by the time you taste it out of your faucet at home, you don't have bacteria in there. So they treat it. They treat it with chlorine. They treat it with fluoride, different minerals in there to give it a different taste, to clean it, just to make sure substances are not growing within that water. If you try Smart Water, you're like, oh, that tastes so much different. They have different minerals in there to affect the taste of the Smart Water. So your waters that you taste, they're not going to typically be 7. They might be like a 6.3. They might be like a 6.2. They might be like a 6.9. Each brand of water has a different pH. They're close to neutral, but they're going to have additives in there for a different taste. Maybe you notice it, maybe not. Maybe you will start to notice that. Check it out. What's your favorite water? Fiji, Poland Springs, Aquafina. Anybody a water snob? Anybody have a favorite water I could try? I love different types of water. As weird as it sounds. What's the best water? Catskills water. No one has a favorite? All right, more information on this. Here we go. Acid bases. What makes an acid an acid? It's the hydronium. So to the right of this, we're going to draw a couple other pictures and we'll call it quits. I'm going to text box to the top right of this diagram. Make sure there's a little space in between because I'm going to add something else next time. So as a strong acid is going to have high concentration of H plus or hydronium, high concentration of H plus, but it's also going to have a low concentration of hydroxide. There's not much hydroxide in this acid. So it makes it a strong acid. There's a lot of hydronium. There's not much hydroxide. I'm going to color code this text box. I'm actually going to color it black for the outline. And I'm going to color code each one of these texts. There's a high concentration of H plus for a strong acid. Make my font a little bit bigger. High concentration, make that bigger. Low concentration of hydroxide. Make this font smaller. It's not as concentrated. There's a lot of H plus. There's not much OH negative. I'm going to copy that same text box right there. I'm going to paste it. I'm going to look at the bases. Look at the strong base. What's happening with a strong base? What makes a base a base? It's going to have a lot of hydroxide. So it's going to flip-flop. There's going to be a high concentration of hydroxide and low concentration of H plus. So this is going to be high concentration of OH negative and a low concentration of hydronium. They shift in this situation. I'm going to change the sizes of my text as well. So the size of it's basically telling you there's not much. What makes an acid an acid? An acid is a strong acid because it has a lot of H plus. There's not much OH minus. What makes a strong base? There's a lot of OH minus, hydroxide. There's not much H plus. I'm going to copy this text box below. I'm going to copy by hitting Control C. I'm going to paste it in there again. Whoops, not there. Let's try it again. Copy the text box, paste it, Control V. I'm going to put this text box at the neutralization or neutral point. What happens here? Someone throw in the chat on mute. What happens at neutral point? At 7. It's a smart group. I know somebody knows this answer. What happens at neutralization point? Oh, yeah. Perfect. Couple answers. Thank you. At this point, at neutral, they're going to be equal. So H plus is equal to OH negative. Awesome. At this point right here, they're both going to be equal. So H plus hydronium is equal to hydroxide. Hopefully you see that shift. They're going to be equal at neutralization. Next class, we're going to add more information on this pH scale. We'll add some concentration values for hydronium. You'll see the factors, how they tenfold increase or tenfold decrease. Once you have this image, please save and close it. Hopefully it saves the first time for you. And that is going to be it for today's class. All right, guys, that's it. Once you're all set, have a great day. Make good decisions. If you have any questions, feel free to ask for help. We'll see you later. Bye, guys. See you later. Acids and bases in life. Oh, you too. See you guys. Bye, Kai. Bye, John. Have a good one. No. No. My picture. Oh, where'd it go? Come on. How's my pH scale's gone? Didn't save. I have to ask someone to send it to me. Is this it? Ah, randomly there. Hopefully you guys don't experience this problem. pH scale. Again, you want it to be this whole page though. So just make sure it's the whole page. We'll definitely add more and more on that next time. See you later, guys. Have a good day.